Hello everyone. In this video you will learn how to determine the maximum moment in beams with different loading schemes. That is part 5, including the following key points that we are going to cover: how to determine the support reactions, construct the shear force and bending moment diagram, and present a simplified method of finding the maximum bending moment under trapezoidal loading using the shear diagram and the method of section. So let's dive into our problem. So the problem is determine the maximum moment of a beam carrying a uniform load and concentrated load of as shown in the figure below. So we have the load diagram. We have the cantilever load subjected for 8 kilonewton concentrated load and a uniform load of 15 kilonewton per meter. And for the center span, we have a 40 kilonewton concentrated load and 25 kilonewton center load. We have also the trapezoidal load. We have that centroid of the trapezoidal. We have the formula for that. And if you cannot remember, you can treat this also into two parts. One triangular, one rectangular, 40 times 2, and the other one is triangular. So the triangular, the height is 20, that is 60 minus 40. And we have also the uniform load from point A to F, that is kilonewton per meter, kilonewton. And we have also 5 kilonewtons applied at the free end of the cantilever beam. So let's get started with our solution. So first of all, we need to determine the reaction at supports, that is support A and support B. So let's say we'll take a moment, sum up moment at point A, positive clockwise is equal to 0. So minus RB times 5. So this is counterclockwise, so negative times the moment arm is equal to 5. So minus 8 kilonewton times 1.2, which is this one here, minus 15 kilonewton per meter times 1.2 squared over 2. This is counterclockwise, so negative. Then plus 40 kilonewtons times 1.5, the moment arm, this one, plus 40 times 2, which is the rectangular one for the trapezoidal loading. We will treat this into two parts. So 40 times 2 times the moment arms of 2.5. So the center line of triangle is 1 meter from here. So there is 2.5. Then we have triangular load here. That is 0.5 times 2 times 20 kilonewton. That is 60 minus 40. That is 20. So times 2/3 of 2 meters, which is this one here, plus 1.5, this one. So that is the centroid of the triangular load from here to the point A. Then plus clockwise 25 times 3.5, that is the moment arm from here to there, 3.5, plus the uniform load, which is 18 kilonewton per meter times 3. So we'll just take it from here, point A, from point E to point F. That is 18 times 3 times 5. The centroid of the uniform load is from here to there, that is 5 meters. Plus the cantilever end, which is 5 kilonewton times 6.5, that is from here to there. So the RB is equal to 137.25 kilonewton. Now we need to determine the reaction at A. So by summing up forces along Y, positive upward, is equal to 0, we have 137.25. The reaction at point B, plus RA, this one, that is upward, positive, minus 8 kilonewtons, minus 15 times 1.2, which is this one, minus 40 kilonewtons downward, that's negative, minus 0.5 times 2 times 40 plus 60, that is the uh, trapezoidal load. So we considered it consider it as trapezoidal because we're just calculating the total load of the trapezoidal loading. So minus 25, which is this one, downward minus 18 times 3, which is from here to there, uniform load, and minus 5 kilonewton, this one. So RE is equal to 112.75 kilonewton. So now we are done with reactions, RE and RB. So we can now start to draw the shear diagram. So to draw the shear diagram, at, at point C, shear is 0. Then we have a dropping load of 8 kilonewtons. So we have to drop to negative 8 at this point, just to the right of point C. So at point A, this one here, we have minus 8 times the minus the load between C and A, which is equal to 15 times 1.2. So the total is negative 26. We have 26 here. So from negative 26, that is the shear at the cantilever end. So just to the right of point A, we have a reaction here, which is 112.75. So negative 26 plus 112.75, we have 86.75. So between A and D, there is no load. So our shear diagram is constant from here. By the way, from point C to A, we have a uniform load. So our shear diagram here is linear. Now the shear at point D, just to the right of point D, we have 86. We have 86.75 minus 40, that is equal to 46.75. So we have here, we have 86.75 minus 40 kilonewtons, so it drops to 46.75. So from this point to that point, we have a trapezoidal loading. So we will just 46.75 minus the trapezoidal loading. So the shear at point E, that is 46.75 minus the trapezoidal loading, which is 0.5 times 2 times the average of 40 plus 60, that is equal to negative 53.25. So we have here negative 53.25. This is the shear just to the left of at point E. Then we have 25 kilonewtons. So minus 53.25 minus 25 kilonewtons. So we have negative 78.25. Then we'll proceed to shear at point B. So the shear at point B is negative 78.25 minus the load between A and B. So that is a uniform load. So negative 18 times 1.5, that is equal to negative 105.25. So this is linear because the load between A and B is uniform. So here we have a triangular. We have a trapezoidal loading here, a first degree. So we have a second degree curve in the shear diagram. So from negative 105.25, we have the reaction of 137.5.25. Then that gives us a total of 32. It becomes positive. At this point, this is the shear at point B. So now the shear at point F, we don't have the shear at point F, but we have a concentrated load of 5 kilonewton that is equal to, if we evaluate the shear at point F, that is 32 kilonewtons, which is this one here, minus 18 kilonewton per meter times 1.5 minus the shear, the load between B to F. So that is equal to 5. But we have a dropping load here of 5 kilonewtons, so this shear here is back to 0. But here guys, we need to evaluate the location of zero shear. So at zero shear, we expect that the location also of maximum moment at this point. So stick around guys, and we will evaluate that how we come up this value 1.04. So now we have determined the reaction at point A and point B. So we can now proceed to draw the shear diagram. So to draw the shear diagram, at point C, shear is 0, and we have a negative 8 kilonewton. So from 0, it goes down to minus 8. Then at point C, at point A, that is minus 8 minus the uniform load between C and A, which is equal to negative 8 minus 15 times 1.2. That is the total load of the uniform load from C to A. So we have here negative 26. So from negative 26, we have the reaction at A, which is equal to 112.75. So minus 26 plus 112.75, that is equal to 86.75. So from point A to D, there is no load, so our shear diagram is constant. Meaning, if you take section any point at this between A and D, the shear is 86.75. So at point D, that is 86.75 minus 40 kilonewtons, that is equal to 46.75. So we have here point D, we have 46.75. So at point D to E, we have the trapezoidal loading. So trapezoidal loading, that is first degree, and we have a second degree curve, which is parabolic. So from 46.75 minus that total load of the trapezoidal loading, that is at point E, that is 46.75 minus the trapezoidal load, which is equal to 0.5 times 2 times the average of 40 plus 60, that is negative 53.25. That is here we have negative 53.25. So at point E, we have a negative 25 concentrated load. So from negative 53.25 minus 25 kilonewton, that is equal to negative 78.25. So this is the shear just to the right at point E. So at B, the shear at B, we have a uniform load. So in our shear diagram, we have a first degree shear, this one here, first degree. So at point B is equal to negative 78.25 minus the load between from point E to B, which is equal to, that is minus 18 times 1.5. So that is equal to negative 105.25. So up here, we have calculated that shear at B minus 105.25. So from point B, from negative 105.5 plus 137.25 kilonewtons, that is the reaction at point B, and that is equal to positive 32. So this is the shear just to the right of point B, where cantilever end. So the shear at point F, that is equal to 32 minus the load between B and F, which is equal to 18 times 1.5, that is equal to, no, we still have to deduct 5, that is equal to 0. If it is so happen that shear at point F are not equal, then you need to revisit your preceding calculation for some inconsistency. So let's proceed to draw the moment diagram. The maximum moment can be determined by calculating the area under the shear diagram, starting from the point of zero shear. So the moment at point C is equal to 0 because we don't have anything here. And the moment at point A is equal to the area under the shear diagram, which is from point C to A, which is trapezoidal area. And that is equal to negative 5 times 1.2 times the average of 8 kilonewton plus 26 kilonewton, that is equal to negative 20.4. So negative 20.4. So in the shear diagram, we have a linear, and the moment diagram here is second degree parabolic. First degree in the shear, second degree in the moment diagram. And that is negative slope because our shear diagram is negative. Now we can proceed to determine the moment at point D. So the moment at point D is equal to negative 20.4 plus the area under the shear diagram from point A to D, which is rectangular. So that is negative 20.4 plus 86.75 times 1.5 from here to there. And that is equal to 109.72. So that is the moment at point D. Now we can proceed to determine the moment where the shear is 0. And that is also the location of our maximum moment. So to determine the distance x location at the 0 shear, we cannot determine it by ratio and proportion because it is a second degree curve. It is a parabolic. So we need to formulate an equation in terms of x. So to sum up shear at point 0 shear, we need to sum up moment, summation of forces along y, positive is equal to 0. So 46.75, which is this one here, minus v minus 0.5 times x times the area of the height of the trapezoidal, which is 40 plus y prime plus 40 from here to there. So that is y prime plus 40 is equal to 0. So by ratio and proportion, we can determine the y prime, and we can express that into the value of x, that is equal to 10x. That is by ratio and proportion. So the equation of shear, that is reduced to minus 5x squared minus 40x plus 46.75. So at this location, we have the condition that shear is equal to 0. So if we equate that equal to 0, we have a quadratic equation, which is x squared plus 8x minus 9.35 is equal to 0, which is x is equal to 1.04 meter. So this is how we come up this value, 1.04 meter here. Now, to calculate the area from point D to, x 1.0 meter, we need to integrate. So, by integrating the equation of our shear, that is uh, minus 5x squared minus 40x plus 46.75 dx. And that is evaluated from 0, from here, 0x, so x is equal to 1.04. So that is equal to negative 5x cubed over 3 after integrating minus 20 times x squared plus 46.75x. So area is equal to minus 5 times 1.04 cube over 3 minus 20 times 1.04 squared plus 46.75 times 1.04. So area is equal to 25.11 kilonewton meter. So that is the area of the second degree curve from x equal to 0 to 1.04. So the moment, the maximum moment at this point is equal to 109.72 plus the area under the shear diagram, which is equal to 25.11, and that is equal to 134.83. So that is our maximum moment. So the moment at point B is equal to the moment at the cantilever end. If we sum up moment at the cantilever end, that is 5 times 1.5 times plus 18 kilonewton per meter times 1.5 square over 2. So that is equal to negative 27.75. So if it is so happen that they are not equal from the if you evaluate the moment, 134.83 plus the area under the shear diagram, if they are not equal with this moment from the cantilever end, then you need to check your calculation, the preceding calculation, it has to be equal to negative 27.75. To explain how we come up this curve in the moment diagram, so from this point we have a second degree. From point A to D, we have a linear because the shear diagram is 0, constant. So the slope here is positive because the shear is positive. And from this point T to the point of where the shear is 0, and that is positive. So from this point in our moment diagram is positive slope until we reach at the point where the slope is horizontal. So that is what we call here contraflexion, the transition between the positive to negative slope. So the second degree shear here in moment diagram is third degree up to this point. That is third degree. So from this point, point A to B, that is linear. So from this point to here, that is second degree curve. Then in the cantilever end at point B to F, we have the first degree, which is linear. So in the moment diagram, it is a positive slope because this is positive shear. And that is second degree curve until it reaches to the point where the moment is 0. So we are done with the shear and moment diagram. Now we have an alternative solution to determine the maximum moment by method of section. So once we have determined the location of 0 shear, we can take the moment directly at this point. If we cut the beam at this point, here, this one, we extract this point C up to the moment, up to the location where the shear is 0. So we have section at 0 shear. So to sum up moment at this point, we have a negative 8 times 3.74. That's the moment arm from here to there. minus 15 times 1.2 times 3.14, the location of uh, the moment arms of 15 kilonewton per meter. So we have also 112.75 positive because it is clockwise times 2.54, which is the reaction at point A. Then minus 40 times 1.04, this one is counterclockwise, and that is negative. Then we have trapezoidal area, and we 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 separate this from rectangular and triangular. So minus zero point 0.5 times 1.04 times 10.4. That is the triangular portion here. That's 10.4 times the moment arm, which is 1.04 over 3. That's the centroid of the triangle. Minus 40 times 1.04 squared over 2. And that is the rectangular load from here to there. So the maximum moment is equal to 134.83. So you will get the same result using the area under the shear diagram and the method of section taking moment at this point. Either you can use this one if you are not comfortable to integrate the this area here, which one is easier for you. So you have a two option to determine the maximum moment. So that's all, guys. Thank you for watching. And if you like this video, please don't forget to like and consider subscribing. See you next time. Bye bye and God bless.